All right, here we go. Sorry, a little bit later today, but we're okay. 11-2 today. 11-2 today. Friday is a B day. So there'll be a day ahead of you guys after Friday. Monday, I got review. Wednesday, I got review. One of those 2 days, we'll go over our Chapter 9 tests, because some of those things you're going to see on the Chapter 9 test, you're going to see on this test, basically with the conditions and the work and the conclusion, all that stuff, okay? One of those days we'll do the Frappies, one of those, and then, but basically we're reviewing those 2 days, okay? Reviewing for those 2 days, and then we're going to test Chapter 10 and Chapter 11 on Friday of next week, okay? I've already assigned 10 review. It's not due until Friday, but I've already assigned it. So if you want to kind of catch up or not get too far behind so you don't have to do a whole lot of stuff, 10 review is assigned. 11 review I'll assign after today. And then I'll have some worksheets for you starting on Monday. So Monday and Wednesday, like I said, reviews, just to kind of catch us all up where we're at. You'll see today is not going to be a whole lot of difference from what you guys already know about the difference in hypothesis testing. You already know the difference in proportions. So now we're going to do the difference in means. Okay. So again, it's a fairly quick lesson, I think. Do remember that we do have matched pairs with means. So whenever we're doing 2 sample of means, it's possible for it to be matched pairs. And so we had matched pairs and 2 sample confidence intervals. That was 10-2. And now we're doing 2 sample means, and we'll talk about matched pairs today also, okay? I jump right into the conditions. Like I said, we already know everything there is to know about significance testing. We just want to make sure we know the conditions. And guys, you already know these conditions, right? Now, we don't have randomness, really. We have 2 independent random samples. Don't remember, right? We got to have 2 independent random samples. And they'll talk about them being independent. They'll talk about them being random. We just make sure we mention it, right? So we have 2 independent random samples, and that's what I typically write: 2 independent random samples, and then I'll go off one to the right and one off to the bottom. So we'll have 26 male students and 22 female students, whatever. Okay, hopefully they're more than 30, but got to mention it. 2 independent random samples. Both samples need to be less than 10% of the population when it's not an experiment. We'll have an example today that's an experiment. We'll talk about the non-10% then. Big discussion on my Facebook group yesterday about when to use the 10% and when not to. So that's what we're going with right now, is the experiments. But both of them need to be less than 10% of the population, and then both of them need to fit the large counts. Okay, both of them need to fit the large counts. And how do we know that? Well, for each sample, the population needs to be normal. Again, guys, you won't see that one. We just put that one for the catch-all, just in case that happens. If the population's normal, every sampling distribution will be normal. We learned that in Chapter 7. If the population is normal, every sampling distribution is normal. If it's not normal, or we don't know what it is, according to the central limit theorem, we want the sample to be greater than 30. If the sample is significantly large, the sampling distribution will be approximately normal. We call 30 our significantly large, right? And if it's not 30, they're just going to give us the data you're going to have to graph, and you'll have to graph both of them. You'll have to graph both of them, unless one of them's more than 30 and the other one's not, right? If one of them's more than 30, you don't have to graph that one, but if the other one's not more than 30, you'll have to graph that one. So one of those 3 things has to happen. It won't be the first one. It will typically be this. Typically, if you have to graph one, you'll have to graph both. Typically, if one of them's greater than 30, they're both greater than 30. I mean, it's just very seldom do those get intermixed, okay? But you got to do both. You got to do both. Because if this one's normal and this one's normal, the difference will be normal. Again, we learned that in Chapter 7. That's why we have to prove that they're both normal, approximately normal. So if this one's approximately normal and this one's approximately normal, and we're going to subtract them like we're going to do, then it will be approximately normal. So, okay with the conditions. Same conditions we've had for the last 3 chapters. And it's going to be the same conditions for chapter 12. Same conditions for chapter 12. Just this is going to be different here. Yeah, how to prove it's different. But you'll have this and you'll have this. Hypotheses for this particular one, because it's 2 sample, mu1 minus mu2 will be equal to whatever that value is. Typically, that value is 0. Typically, we don't think there's a difference between them. I think I can only think of one instance when that's not 0, and that's on one of your homeworks. Actually, it's not even a homework. I think maybe it's a homework, but I have one on a worksheet too that's not 0. But it's obvious. It's obvious. Most of the time, that's 0. Most time we assume there's no difference between the 2 populations. No difference between the 2 populations. And then our alternative, well, we think one of them's less, or we think one of them's greater, or we think that they're different. One of those 3. And again, typically that value is 0. Whatever this number is, these numbers, this one has to be the same, right? If we think that, ooh, that would have been bad. I got in trouble. Let's see. We think that seniors type 3 words faster than freshmen, then that'd be 3. We assume it's 3, and then we might think that freshmen are better or worse than the 3. So that would be when it might be not 0. But most of the time, that's 0. And again, whatever this value is whatever. These values don't change. So if that's a 3, then this one has to be a 3. We can't do 3 and a 4, or 3 and a 2, or 3 and a 0. Whatever they are, they have to be the same. And of course, we're only going to have one of these, right? Only one of those, whatever's in the context of the question. But please, 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 please make sure you define both. Let's get a pencil so I can highlight that. Let's put it in red for blood. There we go. Make sure you define both. You got to tell me both. Where mu1 is the true mean, whatever, of whatever. True mean is what those are the words that I use. True mean, because that means you're referring to the population. And true is a whole lot easier to write than population. But you can write where mu1 is the true population mean. I said true again. Where mu1 is the population mean. Where mu1 is the true mean. Either way, you just got to make sure you refer it to the population, not a sample. Make sure these are never X bars. These are never P hats. These are either mu's or P's. P's for categorical, mu's for numerical. Good enough with all that. I've worn that out. Remember that we can write these in different format. I typically write them like this because that one seems to make a little bit more sense to me. AP typically writes them like this. Just remember that a quick algebra move, I can move that over here and it's the same thing, right? You can add mu2 to both sides. Add mu2 to both sides and then you'll have that one. Or if you write it like this, you can move the mu2 over here. You'll have mu1 minus mu2 is equal to 0. It's just a quick little algebraic move, okay? So this one, it's easier for me to know, hey, mu1's bigger than mu2. I can see that easily here. This one, I have to do a little thinking, right? If mu1 minus mu2 is positive, that must mean that mu1's bigger. And I have to think about that one's just easy. So, but you can write them either way. They don't care. They don't care. Hit me.
Why does that say how, but previously was
Oh, those should be, these should be Haas. Sorry. Yeah, those should be Haas. Good catch. I don't know what I did there. Yeah, those should be Haas. Good catch. Good catch. If I had some cookies, I'd give you one. If I had $1, I'd give you $1. I don't have $1. I used to carry around dollars and give students dollars when they correct me. But then I got tired of losing money because they correct me all the time. I'm not. I'm only wrong once a year. That's just a mistake. That's not wrong. That's a mistake. Good catch, though. Bam. Formula, right? So the formula's in words. You got to turn the words into variables. The standardized test statistic. Well, guys, we're talking about means, so the means will be T's. Means will be T's. Why are means T's? because we don't know the population standard deviation. That's, if you know that, because that's typically a question on the multiple choice sometime. Why do we use T's instead of Z's? Well, because we're estimating two things. We're estimating both of those. And so I need more wiggle room. And so because I need more wiggle room, this one right here is the big one. The population standard deviation is what I don't know. That's why I've got T's. My statistic, well, guys, my statistic this time is X bar 1 minus X bar 2. Whichever one you put is 1 and whichever one you put is 2. Right? That's my statistic. Then it's minus my parameter, which is mu1 minus mu2. There. Maybe that helps you see it. Okay? But remember this, right? Mu1 minus mu2 most of the time is 0. So if that's 0, then they don't write that. Because if mu1 minus mu2 equals 0, they'll just put a 0 here. Just don't get confused by saying that this is statistic minus parameter. It's statistic minus parameter. Parameter is 0. And then we got the big old standard deviation formula, because it's a big old radical, because I don't want the variance, I want the standard deviation, and we can't ever add standard deviations, we can only add variances. So we'll square that variance, and it's over n, not n squared. They're going to try to trick you on some of these multiple choices. Right? They'll try to square the n, they'll try not to square the standard deviation. And then we add, they'll put a minus sign there on some of those too. We always add, we always add. These are 1s and these are 2s. And then we got to take the radical of the whole thing. Okay? So that's the formula that you probably, I mean, again, we've talked about it. You don't have to write the formula anymore with variables, but you need to understand it because the multiple choice will do that. The multiple choice will have these type of options. And so it's your job to make sure you understand how they're getting those values. Very few times does the multiple choice say t equals 2.1, t equals negative 1.6. They typically don't say that. They typically just write it like this so that you can see which one or which one's the correct plugin. So here it is, non-hieroglyphics, right? That parameter is typically 0, not always. Like I said, there's 2 instances where there's not. When it's not, it becomes a big deal. I'll make sure I have to cover that. And then the standard deviation, right? And you have to square the variance or square the standard deviation to get variance. That's still just n, not n squared. We'll square that one and we always add, always add, always add, always add. Always add variances. Highly missed question on the last test, by the way. Highly missed. We'll cover it next week. DF is the crazy one, right? That you're going to get from your technology. The DF you're going to get from your technology. If you can't use technology, you're going to use the smaller of the n-1s. If you can't use technology, you're going to use the smaller of the n-1s. So option 1, we're going to get from our calculator, and it's going to be some weird number that comes from a crazy, crazy formula. Or if we can't use our calculator for some reason, we'll just use the smaller of the n-1s. Both of them are acceptable. This one is not as accurate or precise, I should say, as this one. They both work. This one just gives me a little bit wider. I'm more likely to fail to reject. Any questions? Has the mean number of the mean number of hours Americans work each week changed? Not for me. One of the questions on the General Society survey asked respondents how many hours they work each week. Responses from random samples of employees Americans were recorded for 1975 and 2014. So we can see we have 2 independent random samples. One came from 1975 and one came from 2014. There's no way that those are the same individuals. I don't think. Here they are summarized. For some reason, their sample in 1975 was 746, and their sample here was 1501. And why it was 1501 and not 1500, I don't know, but it was 1501. The mean number is 3897, and this is 4191. So it does look like they are working more. It looks like they're working more. But the standard deviation here is 13. The standard deviation here is 14. So there's actually more variance, which now you can somewhat see, all right, if the mean's more, but there's more variance, there's actually more to the bottom and to the upper than the other one, which is less, whatever. Anyway, that's what they're all telling me. They didn't even ask me a question yet. What's the question say? State the appropriate hypotheses. Okay. Ho. Dot, dot. Mu 1. We assume that they work the same. Equals mu 2. And if you don't want to use 1 and you don't want to use 2, you could use 5 and 4, or you could use 75 and 14. That might be less confusing to you. Older, newer, I don't know, whatever. 1 and 2. And then ha, mu 1, mu 2. Do these data of a difference in the number of work hours. So they don't care that they're working more, and they don't care that they're working less. They're just trying to see if there's a difference. Then don't forget to define. Mu 1, true mean, was it average? Yeah, I think it was average. Average work hours week 1975. Mu 2, true mean average work hours week 2014. Beautiful. Perfectly acceptable. Perfectly acceptable. Any questions about what you might put or what somebody else might put to get full credit or not get full credit?
Can you do the, I didn't look up.
It's okay. Yeah, absolutely. Absolutely. Everybody else okay? Anybody else? I mean, that's like 3 points on your test right there, right? 3 points on your test. Pretty easy to get. Just got to be able to get it. Okay? Here's their work. Ho, they use the minus equals 0. Perfectly fine. They use sub 14 and sub 15. They put 14 first for some reason. Whatever. They don't care. Beautiful. Beautiful. Okay? Explain why the sample results give some evidence. Again, I don't think I've ever seen AP ask this, but here's some evidence. Well, X bar 1 is equal to 3897. X bar 2 is equal to 4191. And those are not the same. They are different. 38.97 does not equal 41.91. That gives me some evidence. That gives me some evidence. Is it statistical evidence? I don't know yet. I don't know if it's statistical evidence yet, but it gives me some evidence. They told me what the difference was, which was 294, which is not 0. That's perfectly, I mean, I think my way is actually a little bit easier than that. I didn't have to do any math. All right, check if the conditions are met. Do I have a blank? No. So I got 2 independent random, sorry, I don't have room to do this, samples. And I'm going to go off that way and go off that way. 764 workers in 1975, 1501 workers in 2014. 764 is greater than 30, and 1501 is greater than 30, and then so large counts is met, or the sample is approximately normal, or the samples are approximately normal. Either way. Either way. However you want to say that. Both are approximately normal, or both large counts are met. Okay? And then, what else do I need? Oh, I guess 764 and 1501 are less than 10% of all workers 1975, 2014. Sorry for that being way low in the back, Matt. I know you guys tough to see that. Perfectly acceptable to write it like that. Right? Just save yourself a lot of, you don't have to write everything down. You just got to get it there. You don't have to write it down twice. It's the exact same thing twice. So I'll break it down. Actually, I guess I should do this and then spread it back out. I don't think you should have just 764 and 1501s less than 10%. I don't think that's going to get it there. I don't think that's going to get it. Less than all workers. Let's see how they did it. Independent random samples of 764 working Americans in 1975 and 1501 working Americans in 2014. Beautiful. I don't think I'd put it much more than that at all. Could put a little bit less than what I put. Look at there. See how they did that? But I combined that and just wrote all this, and then I spread it back out. That's perfectly fine. They don't care that much. And then large counts. Greater than 30, greater than 30. Beautiful. Any questions about what you might not or get there? You okay? Calculate the standardized test statistic. Okay? So here I go. Test statistic, X bar 1, 3897 minus 4191. Minus 0. You don't have to put the minus 0, but I put it there. I like it. Helps me put a placeholder in there. Square root. 38.97 squared. 764. Plus, almost put minus. 4191 squared. 1501. Let my calculator do the work. Let my calculator do the work. Oh, shucks. I should have turned it on. Oh, please come on this screen. There it comes. Huh? Because mu1 minus mu2 is 0. I'm just putting the values in there. Stat. Tests. It's not a t-test, that's a single. 2-sample t-test. Right? If we're asked to write that, 2-sample mean t-test. You'll want all those words in there if you're not writing the formula. 2-sample mean t-test. If it's an interval, make sure we write interval. Don't write test interval. Right? I think I mentioned on a couple tests I had some people write interval test. It's either interval or a test. You can't put both. So hit enter. I don't have the data. I have the stats. And so we're just plugging and chugging. X1, standard deviation, N1. X2, standard deviation, N2. We think it's not equal. We think it's not equal. Never pool. Always hit no on pooled. Always hit no on pooled. Always hit no on pooled. And then you go down to calculate, and it's going to give you the t. It's going to give you the p-value. It's going to give you both. Anybody punch and get?
Yeah.
What do you get?
The T or the P?
Both.
The T is negative 1.65.
1.65. Verified with anybody? Anybody else?
And then for the P, I put 0.09.
I got you right. The one is it supposed to be standard deviation?
Oh, my fault. Yes. Dang it. Another dollar I lost.
I didn't do standard deviation.
You did those?
Yeah.
That's why. Okay, so these are wrong numbers. Now let's fix. Let's fix. Sorry.
T is minus 4.8.
Woo, big number. Woo. 4.88, that's verified? Now, understand this, guys, right? If you flip these two, you're going to get positive. It's okay. They don't care. They don't care. That's why you got to show all your things, okay? My guess, my p-value is really small. I don't know, 0.0000 something times 10 to the negative what? Has it got a little e?
E negative 6.
So that's 0.1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Careful. Please don't ever put the p-values 1 point something, right? P will never be bigger than 1.
We write like to the negative 6.
That's fine. Yeah. They don't care if you write it's almost 0. They don't care if you write that it's really, really, really small. I mean, they really don't care on that. You almost don't need a calculator. If you're almost negative 5 standard deviations away. It's going to be really small. You're almost 5 standard deviations away. That's going to be a really, really small number. And remember, it's doubled. That's doubled because it's not equal to. So a one-sided test will even be smaller than that. So messed up here, guys, right? If you're following along in your notes, these are not, I put means here. Oh, I need an eraser. Okay, those should be the standard deviations. Okay. 13.13, 14.35. Sorry about that. So it looked like I had some evidence. The p-value is really, really, really small. The hoe must go. We got to reject it. There's a lot of evidence. There is significant evidence to say that the mean number of hours worked is different between the 2 years. I bet that's what we're going to ask next, right? So there's that p-value. Again, guys, they don't care. Oh, the DF, I didn't put it. Gosh, I'm going to get minus points. I know I'm going to get -1 on that. Put down what the DF is, right? Now, you're lucky on that one because it tells you what DF is, and then you're more than likely to write that one down. Single-sided, you're not. Single is where you miss it a lot. But that's using the DF of that. See how their t-value is positive. That's okay. They're going to do they're going to go from 4.88 to 99999, but they're still got to double it. So it won't matter. But they just flip-flopped everything. Beautiful. What conclusion you might hit me?
No, I just a refresher for the single. Yeah, how do you find that?
N-1.
Oh, that's all.
N-1. Since p-value less than alpha. Oh, I didn't put alpha. Make sure you put alpha. Put alpha somewhere. So if I didn't put it yet, I'll put it right here. 0.05. They didn't even tell me what it was. It doesn't matter what it is here. You're going to have to reject it. There's no way alpha is 0.000, right? We reject hoe. P is low, the hoe must go. There is, if we reject, there is enough evidence to suggest a difference in the true mean number of hours worked for Americans in 19. That's what I'm going to put. I'm going to go back to the question and put exactly that, because then there's no way for me to mess up. If I don't go to that, I may not put that word difference. I may not put it. You need to put it. That's important. True mean. Right? I want to make sure I refer to the population. I don't want to refer to that sample. You could be really good here about for all Americans. You could be really cool, I guess. But if you say true, you're okay. You're talking about all of them. Because a p-value is less than alpha, we'll reject Ho. There is convincing evidence of a difference in the true mean hour. I told you, they're going to put it just like their question asked. That's where I'm going to put. I'm going to go back to that question, and I'm going to use that as my answer. Make sure I answered their question. You will have a hypothesis test means on yours. I don't know if it's one sample, and I don't know if it's two samples, but you will have a hypothesis test means on your next test. No question. You will have a confidence interval as one of your free response. I don't know if it'll be one sample, and I don't know if it'll be two samples. Those are two free responses, and those are probably the two free responses you're going to have. Confidence interval, hypothesis test. It's either going to be one sample or two sample. It's going to be one sample or two sample. If this one's one sample, this one's probably two sample. If this one's one sample, this one's probably two sample. One of them's going to be one and one's going to be two. More than likely. More than likely. There will be two. I didn't say there's only two. Do I need to go through another one? Large sample of people revealed a relationship between calcium intake. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. What's that going to tell me right off the bat? Don't check the 10%. Don't check the 10% because I did a randomized comparative experiment. I'm using everybody. If I'm using everybody, I'm not putting them back in. The subjects were 21 healthy men who volunteered to take part in the experiment. 21. Dadgummit. That means I'm probably going to have to graph that data. 10 of the men received calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked like identical. The experiment was double blind. Oh man, remember that, right? Double blind. That means I don't know what I'm doing, and the receiver doesn't know which one they got. Somebody knows. The response variable is the decrease in systolic blood pressure for the subject after 12 weeks in millimeters mercury. An increase appears as a negative number. So there's group one, there's group two. Beautiful. Does the data provide convincing evidence? So you would put one of these in L1, you would put one of these in L2. You need to graph both of them. So I just turn one of them on, and then I'll turn the second one on. And the first one I'll have is L1, and the second one I'll have is L2. Zoom 9 them both, and I'll just put them both on the same number line. Okay, so we'll see that. Beautiful. We assume there's no difference. We assume that one of them is greater than, the calcium supplement is greater than the placebo. Make sure you define both. That's 3 points. Make sure we check the conditions. Randomness, approximately normal. They did dot plots. I don't think I'd do dot plots, but you can. Those dot plots take a little bit longer to do than a box plot. But you got to graph them both. 10% is not needed. You don't have to say that it's not needed, but if you do say, make sure you say it's not needed. Don't say it fits the 10% condition. Don't say that. If you want to say 10% not needed, that's good. And if you don't want to say anything about the 10%, don't put 10% check. That's going to get you. Okay. There's X bar sub C. When you do this on your calculator, guys, it's going to give you everything. It gives you everything. right? When you do two SAMP T test, and you go to data and you hit enter, it gives you all of these values. X bar 1, there's X bar 2, here's standard deviation 1, there's standard deviation 2, there's N1, there's N2. It gives you that crazy DF. There it is, 15592. It gives you the T value. It gives you the P value. Gives you all that. You just got to transfer that over to your paper. Just write them all down. Write them all down. Hit me.
So do we have to write the formula if we use a calculator? Or just like the two samples?
So we're going to write 2 sample mean T test. Really, they would like the word difference in there somewhere.
But then we don't have to write that.
You do not have to write this.
Yeah.
You don't have to write that.
We can just keep all
Correct.
Okay.
Good question. Everybody else, y'all okay with that? This is about the time of year where students rather write the name than that formula. That formula is bad. And it starts to write a lot. But now you still have to write down all this stuff. But that's okay. Your calculator gives you that. It doesn't take much effort. You just got to waste a little bit of lead to write it down. But if you don't write all that down, all you give me is the T, that's not going to be enough. That's not going to be enough. And if all you do is give me the T and the P, that's not enough. Give me the T, give me the P, give me the DF, give me X bar, give me standard deviation, give me X bar, give me standard deviation, N1, N2. Give me all that, and then tell me this. That's all they need. That's all they need for the work. You don't have to say, I used my calculator. You know, that's not even going to be graded. They don't care that you used your calculator. Everybody okay? Just recognize, again, on multiple choice, they're going to give it to you like that. Multiple choices, they're going to give it to you like that. And that's kind of why you need to at least recognize it and know it. Square these things, don't square these things. Another thing they like to do is put DF down here. They like to put a 9 and put a 10 here. Okay, just be aware of those type of things. Anybody else questions on the work and what you need for your points? I'm greater than 0.05. Got to fail to reject. Failed to reject. There is not enough evidence to suggest that a calcium supplement reduces blood pressure more than a placebo on average for subjects like the ones in this study. I mean, guys, they're going to tell you what to put. Just put it. Oh, I'm not too sure. Nah. Answer the question. Answer the question. Answer their question. I didn't write hardly any of that stuff down. What question you got? Calculator, y'all okay with? Right, second y equals stat edit, right? You're going to put all your data in L1, put all your data in L2. Stat calculate to SAMP T test. Oh, that's what I need to write down. That's my method. I think they want the word difference in there. Difference of 2 sample mean T test. I think that would just be a little bit booster right there. One of those 0.5s gives you, raises it up a little bit. You got to draw those graphs. You got to graph them. So transfer those graphs over to your paper. Put a couple numbers down just to show that you did it. Okay? Those will actually have 0 in the middle of it because they're positives and negatives. So that will help you graph it. The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like these who take the calcium from men like these who take the placebo. Anybody have questions? Let's talk about matched pairs. Let's talk about matched pairs. Interpret. Remember what that p-value means. Remember what that p-value means. That is the chances It is a proportion. It is a percent. It is the chances of getting a difference of, what was our difference? I don't even know what it was. It doesn't show me. 5.273, because that's what the difference was. Or less. Or greater. It was or greater, because that was we did a right-tailed test. Yep, we did a right-tailed test of getting 5 point, here, let me put it here. The chance of getting 5.238 or greater, and then I got to put assuming there is no difference. Is, I guess I should put is. What was the chance? What was the p-value? 0.0664. 0.0644. P-value, you got to know how to interpret that. You got to know how to interpret that. That's going to be a couple questions on the AEP test, so you know it's going to be some on my test. Rather it be on the multiple choice, rather it be a free response. Assuming, there they put assuming it's true. They did that first. That's okay, as long as you mention it. You got to mention that. Then they mentioned the probability of getting a difference of the two groups of 5.273. I think I put 533. Or greater. That's what they're going to grade. Just by chance alone. I don't know if those three things you got to have. Assuming Ho is true. Assuming Ho is true, there is that chance of getting the X bar we got, or greater. And the reason why it's or greater is because that's what the Ha was. The Ha was greater. If the Ha was less, it'd be or less. If it was not equals to, it'd be more extreme, because it could be more or less times 2. They typically don't ask it for a not equals to. Oh, here's how you do it on your calculator. Okay. Again, always put no for pooled. Always put no for pooled. I don't even want to talk about it. I don't think you'll ever, there's no need. Never use pooled. That's what you need to know. That's what you need to know. Okay, here's a paired one. Here's a paired one. So just look at it real quickly. Okay, I don't want to go through this entire thing. I want you guys to work on your homework. But randomness, you talk about it being paired data. So your conditions, you mention it being paired in the conditions. I don't care about all of them being 10%. I care about the differences being 10%. And I only have to graph the differences. I only have to graph the differences. Or the differences will be greater than 30, and that typically won't happen. Typically, you'll have to graph them. Okay? Mu sub difference. You don't have to put difference, but it's good to. But whatever we think the difference will be, typically it is 0. Typically, we think there's no difference. And then, of course, greater than, less than. I got Haas here, Ethan. I did good there. Give me my $1 back. The formula is just for one sample, guys. The formula is for one sample. So it's X bar minus mu. Typically it's 0. The standard deviation of the differences and however many differences there are. Okay, so it's just one sample. Therefore, DF is n minus 1 because it's one sample. It's one sample. Okay, so this is just like Mondays, right? Mondays. It's just one sample stuff. Okay, a lot of y'all are looking up and writing. What am I going too fast, too slow? Y'all okay? Like I said, I want to try to give you time to work on your assignment. DF is N minus 1. Here, let's read this one really quickly so you can kind of see this, okay? I want you to see this. Researchers design an experiment. Uh-oh, there we go. We got an experiment, okay? Study the effects of caffeine withdrawal. They recruited 11 volunteers. We don't like volunteers, but they used them. It's okay. Who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During 1 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took a placebo. The order in which the subjects took the caffeine and placebo was randomized. At the end of the 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table displays this data on the subject's depression test scores. Higher test scores means more symptoms of depression. This is what I need you to recognize. Here's subject 1. Here's their depression caffeine. Here's their depression placebo. That's the same person. It's not an independent random sample. I'm getting the data from the same individual. So when I'm getting 2 sets of data from the same individual, that has to be paired data. And you need to recognize it, okay? Typically, it happens with a before and after. It happens in this case where you have a depression of caffeine, and so you have a pill with caffeine and a pill without, but it's the same individual. Or they're alike in some ways. Twins, they paired them somehow, and they'll tell you that they paired them. The individuals were paired by age. Okay, they're paired. They're paired. And so I don't really care what these numbers are, and I don't care what these numbers are. I care what the difference in these numbers are. So quickly subtract those, and you can do top minus bottom or bottom minus top. It won't matter. Whichever way you want to do it. Just make sure whichever way you do it, you write about that's the way I did it. Okay? But now we don't have an X bar 1 and we don't have an X bar 2. We just have an X bar D difference. And we'll have a standard deviation of differences. So however you got to get those differences in there. Remember I showed you could put L1 and L2 and do L1 minus L2, and then you can have that in L3. Or just quickly subtract those. It doesn't take much to subtract those and put those differences in there. But you got to do that so you can find X bar and you can find the standard deviation. Yeah. Oh, you had something.
So is the 1 through 11?
Those are the 11 different people. Yeah. And that's, be careful with that, right? I'll get some knuckleheads put these in L1. No, those are just the 11 people. Those are not the values of anything. So be careful about that. Great. I'm glad you mentioned that. Okay. So I just put these in L1, put those in L2, figure out the differences, and then you're just doing a t-test. T-test. One sample. One sample. Okay. We assume that there's no difference. We think it's greater. And the reason why we think it's greater is because we put the placebo first. And there's where they did it. So however you subtracted it. Now remember, how you subtract it is how this is going to go. So if you subtract them flip-flop, you want that to be less than. Just kind of remember all that stuff. They use 0.05 again for alpha, wherever you want to. Again, I don't know why they list it there. They always list it there. I just list it when I do my work. But you just got to list it somewhere. Random. Randomly assigned treatments, placebo, caffeine, boom. Paired t-test. That's your method. Your method is you got to make sure it's paired. We got to talk about the word paired somewhere. We have a paired t-test. It's not one sample. It's not 2 sample. It's paired t-test. And then they used a bar graph this time. Again, I don't really like those. I just soon do a box and whisker, a box plot. Okay. There's X bar sub D. Your calculator will give you that. There's the standard deviation of D. N is 11, therefore DF is 10. Don't forget to put that. Okay, again, that's the more minus ones than any other question ever in this class is minus ones for not putting the DF. Here's the T value. Somewhere on there, there's a P value. They use the table. I don't know why they would use the table, but it's somewhere between that and that. Because the p-value is less than alpha, you reject the whole. You do have convincing evidence. And again, I'm going to go here. I do have evidence that the caffeine withdrawal increases depression score. Hit me.
Where do we put the age on the test?
I assume there's no difference. Assume there's no difference. Here we go, right here. We assume there's no difference between them two. Most time that's zero. Most time that is zero for the difference. There's one example that we talked about typing, where I assume that I'm going to get 3 words better after I take the typing or after I do the typing class. So if I assume it's 3 better, then that's a 3. Okay. Don't answer. Just look. Think in your head. I'm going to give you a couple examples. You tell me if you think it's paired or if you think it's independent. In each of the following settings, decide whether you should use a 2-sample T procedure or a paired T procedure, and explain your choice. Okay? Before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fins that's supposed to be faster to remove. A customer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins. So we think HO is equal to 0. 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or vice versa. The time to remove each type of fin is recorded for every diver. Paired, 2-sample. Y'all good? Enzo, what do you think?
The 2-sample?
Could be. Why is it paired?
Because
Same diver. Same diver has a left and same diver has a right. Or vice versa. You're getting 2 readings from an individual. Okay? 2 readings for an individual. These are hard. These are hard to tell the difference a lot of times. Okay, a lot of times. Especially when you're in the mode of doing everything 2 samples. When they throw a paired in there, it messes with our minds a little bit. Okay? That one's paired. B, study the health of aquatic life. Scientists gathered a random sample of 60 white piranha fish from a tributary of the Amazon River. The average length of these fish was compared to a random sample of 82 white piranha from the same tributary a decade ago. This one should be almost as easy as any of them. Paired, not paired. Avery, you think? 2-sample. And why you don't say it like a question? Why do you think it's 2? They're independent random samples, right? Okay, that's pretty much all you have to talk about. And the easiest way to talk about this one, guys, you can't pair 60 and 82. You got 2 different sample sizes. There's no way for that to be paired. Okay, that's like a dead giveaway of that one. Dead giveaway. They have to at least have the same size to even think about it being paired. Can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. To test this idea, she fills 2 identical drums with bait, covers one in the standard black neoprene wetsuit and the other in the new wetsuit. Over a period of 1 week, she selects 16 2-hour time intervals and randomly assigns 8 of them to the drum in the black wetsuit. The other 8 are assigned to the drum with the new suit. During each time period, the appropriate drum is submerged in water, and the sharks frequent that number of times a bite the drum is recorded. A little bit tougher to figure this one out. Paired, independent. Experiment. It's okay, you still be paired. Are you getting two from the same? Or are they paired prior to, or are they independent completely? Jacques, you think it's two independent? Yep, that's two independent random samples. They're not paired in any way. They would almost have to pair it prior to. I don't know how you could do this one paired other than, I don't know, stick them both in the water. I don't know. I don't know how you could do this one paired. All right, guys. I hope you can state the appropriate null and the alternative hypotheses. Okay, you should be getting pretty good at those by now. I hope that you can determine if the conditions are met. You should be really good at those by now. Okay. I hope you can calculate the standardized test statistic. Calculator does most of the work for you. Okay. Turn it into a p-value. That's TCDF. Okay. Don't forget that. Perform a significance test. And then I think one of the hardest things is to know that it's paired data or not paired data. Okay. Know that it's paired or not paired. Guys, you can still make your errors. You can still have type 1, type 2 errors. Okay. But that being said, your homework should be posted. I think I posted it at 10. Can somebody verify that? Have they seen it?
Do we need to know anything about school?
No. Is there a question on it? Yeah, it was in the notes. Yeah.
But we don't.
No. Just no. Pooled means that they have the population variances are the same. And we don't even know what the population information is. You sure? Did you go next week?